Excellent. So good afternoon. Welcome to this Friday Quantum webinar. Yeah? 2 days before World Quantum Day, which is on the 30th. That's for you. 14th of April. Every year it's World Quantum Day. Yeah? And we're very happy to have Rivan again with us. Yeah? Last year he gave us a nice talk about his master thesis on kernel methods, if I remember correctly, for quantum machine learning. And today, now he's a famous PhD student in Germany, at the Forschungszentrum Jülich. And he will tell us how to apply those methods to industrial applications. Yeah. So, thank you very much for being with us. And please, you're most welcome to share the screen and then start your presentation. Thank you.
Okay, so,
and if you leave your video on, people might see you in a corner.
We'll use it as a mic.
Sorry?
We'll use it as a mic.
Maybe that's better. Sorry, just a second. Yeah, let's see. If people complain, make up better.
So the name of the project is Quantum Computing Enhanced Service Ecosystem for Simulation and Manufacturing, which we never say because that's way too long. So it's QUASIM. Okay, so I'll just first take you over. Let's not show the. Okay, just slow. First go through just what it is quickly and the outline of what the problem is, and then I'll take you through our approach to solving it, and the menu we have, and the preliminary results that we currently have, and then the work we're currently doing to try and extend that. So first, what is QUASIM? So yeah, it's Quantum Computing Enhanced Service Ecosystem for Simulation and Manufacturing. So essentially, it's a collaboration between several different departments in Germany. So there's the DFKI, which is the German Artificial Intelligence Agency, FZJ, which is Forschungszentrum Jülich, which is where I'm doing my PhD, Fraunhofer, IPT, and then Module Works and Trumpf, which are private company industry partners. And the aim of the overall project is to build a framework for how we can use quantum computing in industry. So for our problem specifically, we have this here. So we have the laser cutting of metal. So Trumpf is the company that does this. And essentially they have a whole lot of different objects that they cut out of sheets of metal. And this is just a video of what some of them look like. So it's mostly this, it's just a sheet of metal and they'll cut several different shapes out of one piece of metal.
Sounds like fun.
Yeah. So the problem for us is that when there's a rise in temperature from being cut by a laser, the metal expands. And if this thermal expansion is uncontrolled, it can cause the parts to expand and basically just get stuck or deform. Like the sheet can deform along the side. And that just makes it very hard to remove it from the machine, and it requires manual intervention. So somebody has to come in and fix it. And they want to make it as efficient as possible. They want it to run overnight without human supervision. So that's the physical problem. And then the numeric problem is that with existing methods of numeric simulation, we use finite element methods. which are just really slow and expensive, like we're talking weeks to run a simulation kind of thing on a big cluster computer. So that can cost thousands of euros. So what we get is an object like this as a mesh, which is just its graphs and vertices, and they're meant to represent the objects that are being cut by the laser machine. And we get the temperature of this object at each node at every time step. So essentially, like the laser is going along the edge and heating it up. So we're not even working with real data per se, it's simulations of this laser cutting process, which we're using as our input data. So if we have several different ways which we've tried to solve this problem with so far. So the ones that happened kind of before I got there was just a mesh graph neural network, which is fairly straightforward. We just pass this object into a neural network, a classical one. It does its thing, and it spits out the temperature of each node at every time step. And then we have some hybrid approaches. There's references at the bottom for if you want details on those. But they essentially boil down to using a quantum embedding method on the information before passing the information into a neural network. So just kind of reducing the dimensionality of this object and then passing it into a neural network. And the physics-informed one is basically the same thing, just where the loss function is, we try to base it more on physics, based on like thermal heat equations. And then the fourth one, the parameterized quantum circuits, is what honestly, that's what we're using and what I worked on specifically. So the idea, this is the first one, classical one basically. So this is just where you do feature embedding and then pass it into a classical computer. So there's not really anything quantum going on here. The idea was that you would do an embedding of the classical data into a quantum space, and hopefully that would make the graph neural network process it faster. So our way, so I'll start with a quick overview of quantum machine learning. So in a very abstract way, this is how all quantum machine learning kind of works. So you input classical data into a quantum computer. So you have your qubits starting in ground state, 0 state, and then you have different embeddings. So that's mapping your classical data into a quantum space. And then you apply different parameterized unitary gates to that and take a measurement. And then you pass that measurement to a classical computer where you do your optimization. So that optimization has a loss function, tells you how close you are to the objective you said you wanted to learn. And based on the result of that loss function, it tunes these parameters in the quantum circuit. So usually that takes the form of the rotation of a qubit. So it will tune how much you rotate each qubit, and then you'll run the whole circuit again, take your measurement again, and see how it's already closer, and keep adjusting the parameters like that. So the way we use this is when we have that graph object, we input the temperatures from each node. So we go one node at a time because we can't pass the whole graph in. So we go one node at a time and we pass in the node and all of its neighbors. We pass in the temperature of the central node and the temperature of all its neighbors at the specific time step. And we ask our quantum model to predict the temperature at the next time step. Point by point. Yeah. So one of these graph objects can be easily 10,000 nodes. So for each time step, we're going over each of these nodes. So we're running hundreds of thousands of simulations of this quantum computer just for one time step. It's quite computationally extensive. Yeah, and the output we're looking for is the relative temperature at the next time step. So just kind of visually how this looks. So yeah, for the high number of nodes, we go local, because so a local approach just means going at one specific node at a time. So visually, we would take this node here is the central node we're looking at, and then it's 3 neighbors, and we use that to predict the temperature of that node at the next time step. And this is also fairly similar to how finite element methods work, which is also why they're so slow and expensive. So to visualize this on the quantum circuit, how we're actually mapping it, you can see our circuit here. So the number of neighbors can vary in these objects. So some nodes are going to have 4 neighbors. In some of our models, it goes all the way up to 23. So in those, we need 24 qubits just for one circuit, which is also quite a problem to simulate. But yeah, so we take the central node that goes to our first qubit. We use rotational embeddings just to embed the temperature values. And then we basically have parameterized rotations here, and we had entanglements for controlled Zs. And then repeated layers. So this was the model that I was given when we got there, and we've improved on it since. So you'll notice that it's got 2 layers, but there's no data re-uploading or anything like that. It's just another controlled rotation, another entanglement. And so this was the first iteration of our model. And so it's just another visualization of how it predicts, and then we get an output for the next time step, and then the next run through of the model, you then start at time step t=1, and you do the whole process again to get to 2 until you've reached the end of the simulation. And that varies for what piece of metal is being cut. Some take a lot more time because it's a thick piece of metal.
So this was not yet variation.
So it's semi-variation. Yeah. So they did try and tune these control rotations, but it was, I guess, quite the most naive approach to it. There was not really any optimization or anything. Yeah, so this is just the general way of stating it, because like I said, the number of qubits is variable depending on how many neighbors there are. So this is our circuit the way it was. So we have an encoding block, and then you have parameterized layers. Most of the time we've stopped at 2 just because of how computationally expensive it is. And then we take our measurement and map that back to the temperature. And then this is it folded in. So we have the temperature doesn't go directly in. We do a little bit of pre-processing of the variable before it gets rotated. And then, yeah, we have a lot of parameters depending on how many qubits you have. You have 1 rotation on each qubit at least, and another parameter for entangling into the central node every time. So the 2 problems we had with this model is that it wasn't reusable, as in you would make a model for all nodes with just neighbor 3, and then you have to make a separate model for all nodes of neighbor 4, etc. And that's not very efficient because it's all the same object, right? So you expect a lot of the properties to be the same. And the other problem was that it didn't have any symmetry. So when you pass the node and its neighbors into this graph, there's no distinct way of how you should order the neighbors in terms of, like, so we always put the central node as the first qubit, but there's no rule that says which one should be the second qubit, the 4th, 5th. So basically it wasn't invariant to permutations. So what we did to fix that is inside our model, when we had these rotations and controlled Z gates, we actually fixed them all to be the same parameter. So that was good because it meant we could order the neighbors in any way. And we also significantly decreased the amount of parameters that the model had to learn. We found that when you did the learning, they would kind of all converge towards the same parameter anyway, because it was invariant. So when we just fixed it, it kind of speeds up the learning process. So that was the first thing we did. So in this diagram here, theta DC is the central node parameter, so that's its own parameter, it's just for the central node. Dn below it here is the parameter for rotating the neighboring nodes, and DE is the parameter for the edge, so the connections on the graph. So it connects the neighboring nodes to the central node, and then we take a measurement at the end and map it back to our equation. And then we also came up with a variation on the subsampling. So the problem was that the degree of this graph keeps changing, and that's not very useful and much more computationally expensive. You have to keep making new quantum circuits. So we basically came up with a way of fixing the number of qubits. And so we looked at all of our data and said, okay, this is on average how many neighbors each node has. So we're going to fix it at 5 qubits for one node and 4 neighbors. And then if there is not enough neighbors for each qubit, then we consider second degree neighbors. And if there's too many, then we just take the hottest neighbors. So that was just a way to try and control the amount of computation time needed and keep the resource down. And so what we've come up with since then is basically just remeshing the graph we get. So that basically, you pass it through a filter kind of basically, and it spits out the same model but with fixed degree neighbors. So every node will then have 3 neighbors, let's say. And so that's a different way to achieve the same thing without losing data, because here we have to cut some off. And it's often at the most interesting parts where there are multiple neighbors because it's trying to capture complex geometry. So our training and evaluation of this circuit, the model we ran. So this is our loss function. It's basically just a mean squared error between the actual temperature and the predicted temperature. Always looks more complicated in mathematics, but we basically, every time we run the circuit, we compare the prediction we got to what the actual value is from the simulation we have, and we see how far off we are, and we try to make that number as small as possible. And we do that by changing the theta values in the circuit rotation. And then the other thing we have is inference. So during the way the whole program kind of works is that they want to be able to give us just the initial state of the object and the path of the laser, which means our model has to be able to infer every time step in between and guess the correct temperature based on its own inference from the previous time step. So we have to use a mean squared error to show the inferred temperature. So in the training, at least, to be able to say in the in-between steps, how accurate is it, and is it making correct predictions based on predictions that previously made, which is not something you usually have to do. Usually you try to guess as little as possible. And so these were our model assumptions when we were running it, that the gap between time steps would be equal, and that we'd only be using one type of material at a time. So we only trained for us on, I think it wasn't the mild steel data set. So that just meant we didn't have to worry about things like conductivity and thickness of the material and things, just to try and keep it as simple as possible. And so we had 28,000 MAC files and anywhere from 1,000 to 200,000 nodes. with 4 time steps and a max degree of 28. So we for
max degree of what?
max degree of 28 means that the maximum number of neighbors per node is 28. So yeah. And so we only considered for our initial training the graphs with under 2,000 nodes, and then we tried it out with the 5-qubit model that was fixed, and one where it could just keep going up to 24 qubits with separate graphs, separate circuits for each graph. And we also ran it with anywhere between 1 and 4 layers to see if the results improved or not. 30 epochs with an atom optimizer, and so these are the results that we got. So the classical graph convolutional network had 67,000 parameters with a 3.9 validation loss, and so its training time was 1 second per epoch and 0.02 seconds per prediction. So it's pretty nice. Like that, you can run on your laptop. It will be fine. For our model, so the first quantum GNN with degree all means the one that can go up to 24 qubits. So that had a validation loss of 0.85, which is a lot better than the graph neural network, which is good. But the training time, as you can see, is 260 times longer. It's not so good. And the inference time also is 2.15, which is very long. But our model, which we fixed to 5 qubits, actually, so it had 6 parameters in total. So yeah, so it actually had an even better loss of 0.71, and then the training time per epoch 6 seconds, which is still 6 times longer, but much more reasonable. And also all of these were done in penny lane on our cluster, so on all classical simulated quantum computers, not on a real one. And a prediction time of 0.35 seconds. So a much more reasonable result.
Instead of
yeah. Again, with the limitation that we only gave it the small data sets. It was all under 2,000 nodes. And there's some that have 100,000 nodes. So it is still limited to small data sets, but I think it performs fairly well given the limitations. And here you can see a visualization.
Yeah, already twice.
See, just completely disconnected everyone. Cool. Yeah.
Oh, that's quite unstable. Yeah, business.
Okay, so here you can see a visualization of the 3 different things. So on the left is the FEM model, so that's basically our raw data that we're passing in the start of the model, the classical convolutional neural network, and our quantum one on the right. So basically what we're looking for is that they look the same. That's the best we can really hope for. And the news is it mostly does. So this is obviously quite a simple geometry and things like that, but yeah, the inference time is longer, training time is longer, but the good thing here is that the loss is actually less. than the classical model. And the root mean square loss, so that's the loss from the inference in the in-between time steps, is basically the same, which is also good. So from here, then this is when we tried increasing the number of layers. So those were all for one-layer circuits as all the results. For the two-layer circuit, it actually did even better. But the 3 and 4 layer circuits did really badly comparatively. You would expect them to at least be the same. But we think that's more of a coding problem than a model problem. We didn't implement it properly. So that's why we're not focusing too much on these results yet until we can be sure about them. And then the future model, so how we're improving. So the first step is to add the data re-uploading in the layers. So that means basically, in our circuit, we have a encoding block over here and then a parameterized block. And then we just repeat that again. So we have another encoding block, which means you re-upload, so re-embed the same classical data into that qubit again after it's had some work done on it. And then have another parameterized layer, and then you can repeat that as many times as you like, or as many times as is necessary. And some of these we've done tests, some we haven't, but we don't have proper results yet, so I can't show you that yet. And so the pros for this is you get a larger expressivity if you have the data re-uploading, which essentially means the family of functions which your circuit is able to predict is larger, and it's a fairly easy thing to implement into the circuits already. But the cons is that you have a larger circuit depth, so for simulated quantum computers, that's not too much of a problem in terms of error, because we just don't use error. We assume ideal quantum computers. But it does that increase the simulation time, because you just have more computations to do. And then the other thing we want to do is include the distance information. So inside these mesh objects, each node has a temperature on it, but it also has a position. So using the position, we can say how far away they are from each other. And based on physics, we expect that if they're closer together, they should spread heat to each other more than if they're further away. And also, when we ran all of this data in the classical graph neural networks, we're able to see how important each parameter is on the outcome of the model. So when we did that, temperature accounted for 90% of the prediction, and distance accounted for around 9%, and then all the other things like the material and thickness and things like that made up the rest of the 1%. So, I'm just, sorry. Okay, still good. So we figured potential 9% increase in accuracy is worth trying to add into the model. So the first way we've tried to do that is by adding an additional qubit into the circuit for each node. So when we have, this first qubit would still be the central node, then for each neighboring one we'd have a pair. So the first qubit would embed the temperature, the qubit, the second one would embed the distance between the central node and that node, and then you would do a controlled Z rotation between the node and its distance, and then repeat the circuit as it was before. So you just try to add that distance information in somehow. This obviously has the con of needing an extra qubit for each node. So for the ones where it's 20 qubits already, it's not going to work. But for our fixed models, it's still relatively feasible. You can make an 8 or a 10 qubit circuit if you know it's going to stay that size. Then the next is to just make a new variable. So essentially you take the distance and the temperature, and we've just divided the temperature by the distance. Throughout testing, it was close enough to the right ratio. And then embed that at the start of your circuit, so you have a hybrid variable, but you at least know how you got that hybrid variable, which is what we think is more important than just throwing it all in. And then repeat the circuit as it was. And the third option is to, when you have your control Z rotations between the central node and the neighboring node, is to have the parameter be influenced by the distance at that point. So here, also having that 1/r relationship in the parameter. And from our preliminary testing, it's given all these methods except the new variable have given us the same loss, which not what we wanted, but also not too unexpected, because it should only make up at most 9%, and we're still also constricted to small data sets right now. So it's more a proof of concept for right now, and then when we pass it to the full data sets, then we'll know that at least it should work in theory, and we should be incorporating this information as well. And then also a way to include the material properties of the conductivity, things like that, is at this point you just have to add another qubit for those, because they are separate dimensions of data, but they thankfully stay constant. So you know you'll just need one qubit for the whole circuit, because every node will have the same conductivity or the same heat, something like that, and the circuit basically stays the same, and either at the start or the end, you just entangle it, the new qubit through the central node to get some sort of inference from it and take the measurements. And then, I don't have slides for this yet, but the other thing we're working on is trying to reduce the number of nodes we use for training. If you think about it, if the object's only being heated up at one point, you don't need to pass the entire object through for prediction. So we're basically coming up with algorithms to select which nodes need to be affected by the training, and like have a growing graph over that. Questions?
Okay, thank you very much. Other questions? Please speak towards the screen so that the 15 people online can hear as well. Any questions?
One?
Yeah.
So, for the computational cost, obviously the amount of nodes and the amount of neighbors each node has increases the computational cost.
Yeah.
But which one scales it more? More neighbors or more nodes?
With the initial model we had, more neighbors scaled it more, because it would have to create a whole new circuit. So even just like on the penny lane backend, now it's like leaving this, it's creating a new circuit, it's like initializing the whole new one. So that's why it's preferable to keep a constant circuit for all the different training. And then if you also think about it, you might only have 10 nodes with like 12 neighbors, right? So your training set size is really small at that point, and you can't necessarily train anything accurately with a training set that small. So it would often be really computationally expensive and really inaccurate. So yeah, it's best to avoid that as much as you can.
And then there's a video I saw recently where it's a chess problem, where the knight has to move the chessboard.
Yeah.
Only hit every square once.
Yes.
Can this kind of be used to maybe solve that problem?
I haven't thought about it, but
yeah.
I have seen the chess
do it.
problem. Yeah. Well, I mean, I know that quantum computers in general are used for, like the traveling salesman problem and stuff, which is like a path optimization problem. So I guess if you could alter it
Because there as well, we have 64 nodes,
Yes.
and then maximally 2 neighbors, and minimally 2 neighbors, maximally 8.
Yes.
So it's similar setup, but it's a difference in prediction.
Yeah.
That's part of optimization.
Those types of problems are also usually done on quantum annealers, which have many more qubits, like functionally. So it's more feasible. Like they have on the order of 100 to 1,000 qubits.
Any other questions? Yeah, please.
Yeah, just on the conceptual problem work, how the data is. So trying to understand how the data is encoded.
Yeah.
You just have that central qubit which you encode the temperature on, and then all its neighbors, and you also encode their temperatures.
Yes.
And then the idea is to predict the temperature of the central node the next time step.
Yeah.
So how does this connect to the path of the laser?
So the laser tells you which nodes are going to heat up in the first place, right? So if you have the path of the laser, you can say, okay, at time step 1, it's node X and Y that are heating up. So in the next time step, we really need to predict the neighbors of those nodes to see how much their neighbors, like the heat spreads from that initial laser point.
Yeah.
And then in the second time step, you would have to consider where the laser is now, and then all the nodes that were affected in that first time step. So kind of spread out like that.
Yeah.
But that's still a much smaller set than the entire object.
But so depending on the path of the lasers, like which nodes you're going to do the predictions on.
Yeah.
But do you then just start from the beginning, like what you know that the temperature of the laser is, and then just run that forward?
Yeah.
Okay. And then is the larger idea to try and simulate the path, or simulate something to catch a defect in the metals might happen, or?
So our specific part is just to tell them what the temperatures will be.
Okay.
I think if you're really concerned about that outcome, you would still use classical computing at this point, because it would just practically be more reliable for the larger data sets. But they said they want temperatures so that if they have that information, they're able to tell whether it will perform or not. So our model stops at the temperature prediction.
How accurate is the simulated data, and where is that based on physics principles, or is it based on harvested information?
So it's mostly a physics simulation.
Okay.
The accuracy is, I'm not 100% sure. We're just kind of being given it, so we have to trust that it's accurate. We have had 1 or 2 hiccups with it, but we've been able to tell them they've fixed the simulation. And so according to them, it's accurate enough that the results can be implemented in their physical machines.
And in the real production, they use finite element.
Yeah, so the data is coming directly from them.
And they don't use not even the classical machine learning.
No. So we have the BFKI, the German artificial intelligence. They're doing the classical machine learning aspect of this. We kind of work with them and then compare our model to theirs. So the classical model here, that came from them. So we can compare it directly.
And are there any quantum version of finite element methods?
So a different part of this project is kind of working on that. So they're using a different part of the industry, but they're focusing on that. And they've also done simulated quantum algorithms and kind of trying to fill in the gaps to be able to do a FEM quantum computer. But still in the I think the paper might be on archive now.
Okay. Oh, will you share it?
Yeah.
A question pop up.
Sorry. I think I lost all the chat when I lost the connection. On Zoom, it doesn't remember the chat.
It's this graph simplification process to get 1 node and 4 neighbors using only limited info from second order neighbors unique to quantum, or is it feasible to apply classically? I think it is feasible to apply classically, but you don't need to in the classical method as much because you have the resources. It's a method we came up with specifically because we were so restricted with the resources to be able to pass this large graph data into a quantum computer.
Any more questions? Any other questions from the people online? Please, yeah.
Yeah, on the like fixing the angle in the layer to make it like permutation invariant.
Yes.
Does it make a permutation invariant? Like, don't those like the CRZ or the controlled rotations, like they don't commute with each other, right?
So I guess what we mean by invariant is invariant in terms of how you embed the neighbors. Like they can be in any order.
But isn't it like the one on the bottom gonna get a different kind than the one that's like right below the central one? Because like and you're untangling like rows
So
as you do.
it's still happen. I guess it's as invariant as you can get it. It's not truly invariant. A circuit won't always have exactly the same result. But we so we read like in another paper as well, like that tested it out that models often if you give it this type of data that's invariant and you pass it through, the parameters often converge towards the same number anyway. So we said it's probably a fair enough assumption to just fix it from the start.
Yeah, and if you're like on multiple runs you're getting the same accuracies, then probably that doesn't matter as much. So again, what's the variance on like if you run it like small and that training loss that you got?
Okay, any more questions? Please.
Just one. You mentioned moving forward. Obviously, you're refining the formula, refining the method. The assumption you used here was 2,000 nodes, correct?
For now, but we have the bigger data sets up to like 200,000.
Okay, so the scalability of what you're doing now to get to that 200,000?
So if we fix it at 5 qubits, then we're fairly sure we can process the larger ones. It will still obviously take much longer, but we have like quite a lot of computational power and cluster computers, so we can kind of leave it running for a week if we need to, which is nice. And at least test to see if we can process. Like if we can't, then we also at least can say, like, with the current state of quantum computing, we're limited to data sets of this size.
But do you have a feeling for what the speed up could be compared to the classical machine learning?
So at this point, I don't think there would be a speed up, but we're hoping it's more accurate in its predictions. Because I mean, like we're so far away from running this on a real quantum computer, and I don't think the speed up's really meaningful until you can run it on real hardware.
You can estimate the scale.
But I haven't seen in any of our work that there's definite speed up in that sense. It's more an accuracy, which can obviously be valuable in its own way. If they want to know exactly if the machine's going to be formed, they probably want the accuracy more than the speed.
Also, on the computation and the implementation of Pennyline, did you use Pennyline like vanilla, or did you use their like their JET compilation?
I think the vanilla one was PyTorch.
Okay. It's a cool engineering problem from that perspective.
Yeah.
And I also, why I asked was because for me, Pennyline has also been like very fast.
Yeah.
Like these kind of things that work quite well, and I think that nice, like recently added like this new, they're following the MLIR techniques. And so I don't know if it's out yet, but they're like trying to make, make it like almost like Judah, where it goes much quicker, and then you just wrap everything that you have with like AppJet or something. I don't know if it's out yet, but that can be cool to see if that gives you a speed up in time.
I mean, even from the model we were like kind of given when I joined to now, we just with just penny lane speed ups, I think we made it go like a factor of 100 faster.
Yeah.
Okay, thank you very much, Rivan. Thank you very much.